Thank you very much, everyone out there, for joining us this evening for the 4th annual Forest and Fire Learning Series. This is going to be part 2 in a series of 5 taking place every Thursday in April this month from 6 to 7 p.m. Thank you. Let's see. While we kind of get settled in and I kind of give you a quick background to the learning series, I am going to share my screen here. I'm going to bring up this question that we have here for you. We want to know where you're joining us from this evening. So if you wouldn't minty.com and use this code here that you see up in the upper corner. So and I just got, let's see, I think Zoom just crashed on my end. So hopefully we'll be able to stay connected with you. Having some technical difficulties. Thank you for your patience. Let's see. Dana, are we still good? Can we still see Menti?
I cannot see Menti.
Okay. All right. So we'll go ahead and if you wouldn't mind just actually just sharing in the comment section where you're joining us from. We'd really love to know where you are and where you are coming from this evening. So in the meantime, I'll go ahead and let you know that this, again, this virtual event is the second in a series of 5 taking place every Thursday in April. And this event is an opportunity for us to invite county planners, land managers, academics, researchers, and other experts to talk about the effects of fire on our communities and in our forests, on our watersheds, on air quality and fire mitigation strategies for our communities, and how we can, as a community, come together and think through how to become a more resilient community as we live with fire. So a little brief background to this event. It started in 2018 as much of the Southwest was experiencing exceptional drought. And Mountain Studies Institute, whom I work for, came together with other local partners to engage our community and think about how what the current state of our forests are and how we can address the challenges that are facing our forests and our water systems and our natural resources. So this was born the Forest and Fire Learning Series event. And we're really excited to have this evening's speakers with us, Dr. Chuck Rhoades and Scott Roberts. My name is Emily Swindell. I work with the forest team here at Mountain Studies Institute, alongside Dana Hayward, who's working in the background here, making sure that this event moves along smoothly. So thank you, Dana. And as I said, tonight is the second in a series of 5 that will be taking place. And I'm going to see if I can resolve some of my technical issues here and pull up. Here we go. All right. Here we go. Thank you for your patience at home. We really appreciate it. So I want to say a very special thank you to all of our sponsors. You know, we really can't do this without them. We can't bring these kinds of events to you without all of these sponsors, without all of the support of these local entities and stakeholders and collaboratives, and also our partners in the federal government. So let's see here. And thank you again for, I'm having some technical issues, so I might just go ahead and let you know. I'll just go ahead and go without the PowerPoints. I'll let you know that we have a survey that's going to be in the comments section, wherever you're joining us from. And that survey should take about 2 or 3 minutes to fill out, and it really helps us gauge how we're doing and how we can bring more information and topics that you're interested in hearing about in the future. So, and if you do enter that, you will automatically be entered to win a myriad of like a collection of prizes from some of our local partners here that include San Juan Mountains Association, Durango Outdoor Exchange, Pagosa Mountain Sports, Mountain Studies Institute, and Maria's Bookshop. And so in order to win one of these collection of prizes, then you must be 18 years or older, fill out our survey, and also like or follow us on Facebook or YouTube if you haven't already. Awesome. And it looks like Dana to the rescue here, sharing, screen sharing here. Thank you, Dana. So we just went over the survey, which should be in the comments section. These are our sponsors here. And so the next slide will show some of those prizes that you could be entered to win by filling out our survey. So I think we'll go ahead. And if you are the lucky winner, we're going to contact you directly and allow you 1 week to respond in order to claim your prize. Okay, so on to tonight's program. Tonight, we're going to be learning about the connection between wildfires and water systems with Dr. Chuck Rhoades and Scott Roberts. And after their presentations, we'll go ahead and open it up to your questions, which you can type in the comments section at any time. My colleague Dana Hayward, who is working again behind the scenes, will be queuing up your questions for our speakers. So our first speaker is going to be Dr. Chuck Rhoades, who is a research biochemist with the Rocky Mountain Research Station. And Dr. Rhoades' research evaluates biogeochemical linkages between terrestrial and aquatic ecosystems in managed and unmanaged areas. Much of his work addresses the role of upland and riparian soils and vegetation in regulating nitrogen and carbon retention and export from forest watersheds, and how natural and anthropogenic disturbance alters these processes. Speaking with Dr. Rhoades this evening is Scott Roberts, aquatic ecologist with Mountain Studies Institute. Scott Roberts has over 10 years of experience as an aquatic ecologist, field biologist, and geographic information systems analyst. His work experience spans across the US, including the Southern Appalachians of North Carolina and Tennessee, the Rocky Mountains of Colorado, the deserts of New Mexico, and the Sierra Nevada mountains of California. Scott contributes his expertise in aquatic ecology, landscape ecology, and spatial analysis to Mountain Studies Institute. Scott lives here in Durango with his wife and son, and will hopefully get back to touring around the West soon with his band, Sweetwater String Band. So thank you both so much for sharing your research this evening, and I'll go ahead and hand it off to you, Dr. Rhoades.
Great. Thank you. And let's just sort of double check we have things working, since we're having kind of a glitch-filled evening. You guys see me, you see, or not me, you see my slide, and you see my little cursor. I want to make sure that you realize that this is not a picture of me. I'd like to think it is. It may be a picture of Scott. I don't kayak, unfortunately. So keep that in mind. And I'm sure as a Forest Service employee, I probably couldn't do that anyway. But anyway, it's great to be here tonight. And I'm really looking forward to this session and sharing a little bit with you. I bring greetings from the Northern Front Range over in Fort Collins, which is where I work for the Forest Service. And we're looking forward to getting out and starting to see what last year's fires kind of dealt us in terms of water quality. This is a picture from following the High Park fire, which was the last big fire that happened right outside of Fort Collins. This was about 60,000 acres, kind of no big deal, or a big deal at that time, but compared to the 2020 fires, kind of no big deal. But you can see the really nice water quality effects of that fire. So anybody that lives in Colorado and probably surrounding states, probably by this point has gotten a good connection between water quality and the condition of our forests. We live in a headwater state. A lot of us live in headwater catchments, places where our water is derived. Again, this is a drawing of the Cameron Peak, a map of the Cameron Peak fire. Chambers Lake is in the middle of this. Peterson Lake is over here. There are a number of reservoirs in this fire that directly supply water to several 100,000 people along the Front Range. There are diversions and conveyances that run through this fire, and storage facilities that are susceptible to changes. So it's an area that most people, unless you're fairly new to Colorado, are fairly aware of this. And so today we're going to talk a little bit about this. And what I'd like to do is give kind of an overview of some of the short and longer term effects of fires on water quality. And then Scott's going to dive into some of the work that he's been working on, specifically on the 416 fire, which will be a really great local case study. Great. So wildfires have effects on fires starting even during the fire. So last year during the Cameron Peak fire, we were made aware that there were actually some fire retardant and slurry bomber activities that were influencing some of the catchment. So you can see this is the map of the Cameron Peak fire, and these pink lines are places where there had been slurry deposited. And in some of these areas are within, the main idea is to catch fires as just crossing out of a catchment, and usually to avoid riparian areas. So they blue line these areas like they would, and they try to protect them. In this case, where I have my cursor, the fire was moving towards the town of Red Feather Lakes, and there was a lot of concern, and they made a decision that they were going to allow this slurry to go into the stream. This was especially interesting and of concern because it's an area where there is a native cutthroat trout population, and there's been a lot of work trying to protect that population. So fish biologists and local ecologists and the Trout Unlimited local stakeholders were very concerned. Slurry, which I didn't realize, and you might not know, is very high in nutrients, and it contains about 1,000 parts per million of phosphorus in it, which is several orders of magnitude higher than what's in streams. Usually in the Cache-la-Poudre River, there's virtually no measurable phosphorus in the stream. It's taken up by periphyton, and it's kept at a very low level. But when this went into the stream, you can see the immediate increase in this fish-bearing tributary called Roaring Creek, and downstream in the main stem of the river. Hopefully that will be a very short-term effect, but you can see where some of this red slurry is building up in the riparian vegetation. And so there's some possibility that this might have a longer-term effect. A more common response, something that most people have seen, and our happy kayaker was in the middle of in the previous slide, is this ash movement, which we were seeing even following some of the initial rainstorms last summer, following some of the fires up here. This is Chambers Lake. I showed you a photo of this a little while ago, and this is this ash and slurry was making its way down into that lake. Here's some ash that's moving around following the Hayman fire. Ash contains high concentrations of many cations, metals, obviously carbon and char, and you can see large spikes in the electrical conductivity following fires. So this is following the Hayman fire. You can see in the months after the fire these large spikes. We would see this for calcium, magnesium. You might see it for metals as well. And even in some of the unburned areas near the fire where you have had ash blowing around, you can see this. So this is kind of a broad effect. Down in Fort Collins, we've been getting ash that's blown from the fires, and we're seeing that showing up around the edges of reservoirs. So this is definitely sort of one of the initial months to year effects. There can be erosion, and we expect this summer, if we have high intensity rainstorms, we'll see big erosion events. That is a big concern for sediment and blocking roads and safety and so on. It also contains nutrients and carbon, and that may be something that is of concern. So a study we did following the Hayman fire and various other fires in the West captured the amount of carbon and nitrogen that was eroded with these sediments. What we found was that the numbers decrease very quickly, which is something we've seen with other erosion studies. Usually within the first couple of years, as sites revegetate, the erosion pulse slows down. The initial numbers in year one are fairly impressive, 10 kilograms per nitrogen, but that's about twice of what you might get in a year with nitrogen coming in rainfall. So it's a decent number, but it probably isn't going to be something that will reduce the productivity of these soils over the long term. It's something that is much smaller, say, for example, than the amount of nitrogen that's lost in the initial plume of the fire. Something that was done recently by a CSU master student, Bryce Pulver, who's worked down in the 416 fire, was to look at some of the metal concentrations in tributaries coming out of the 416 fire. This was in 2019, the year after the fire, and what Bryce found was pretty interesting for a broad suite of metals. We saw increases that were significant and especially of concern following storm events. Now, this isn't a surprise, but it's good to be able to capture this and be able to come up with a good story and to actually sort of, quantify this. I believe Scott's going to talk a bit about some of the metal accumulation work that he's been interested in down in within the main stem of the river. These were tributaries up in Hermosa Creek, and some of these limits, especially for during the storm events, were of human health concern and certainly something that would affect aquatic biota in terms of things like metal and chromium and cadmium, things that are potentially toxic. So this is something to be aware of, especially in areas where you've got mineralized geology with lots of natural metals in them. Okay, so those are some of the sort of short-term 1 year or less kinds of processes. What I'd like to talk about a little bit is sort of some of the lasting effects and why we see those. So when fires burn, they not only deposit stuff, but they influence the ecosystem. And these are slow-growing ecosystems. Forests are century-aged creatures, and so it takes a while for them to recover. When forests are burned, they stop taking up nutrients, so they stop taking up the nutrients that might make their way down to the stream. Soil supply changes after a fire because you've increased the temperature and moisture coming into these systems. So basically, you've changed the balance of nutrients coming in and going out. In undisturbed systems or in pre-fire systems, usually the quality of the water in terms of the nutrients in that, the nitrogen and phosphorus, are very limited because most of those nutrients are taken up. They're highly demanded by the plants. So the plants don't let them go, we can say. Something that I'd like to kind of make sure that you capture and learn from this talk is that fires are not all the same, and they vary extremely highly across space and time. And so people that study fire spend a lot of time talking about and mapping the fire severity, which is a way that we talk about how much of the vegetation and organic covering has been consumed in a fire. And as you can imagine, the more of that litter or organic matter that's burned off, the more that those mineral soils are exposed to rainfall, the more extreme those effects are. And so you'll hear people talking a lot about moderate or high severity fires, and those are the types of fires. You can see pictures here where the soils are fairly highly exposed, and that's a concern for erosion. Here you can see the great variety of fire severity conditions catchments that may not burn at all, have not burned at all, to catchments that burned in their entirety. And so depending on where you're sampling water quality, your effects would vary substantially. So for example, following the Hyde Park fire on the left and the Hayman fire, we had various effects on stream nitrogen and nitrate in this case. I talk a lot about nitrate because it's the soluble form of nitrogen that leaches readily, moves through subsurface waters into streams, and can influence downstream biota and water treatability. So what you can see is this relationship between the amount of the watershed that was burned at high severity and the stream nitrate in the years following the Hyde Park fire. Similarly, for Hayman, unburned fires, you can see sort of the patterns of the annual patterns in nitrogen for several years following the fire and in the year before it. And then you can see these big increases in areas that burned less than 30% for this low extent and then greater than 50%. So you can see that even after 5 years, things were still coming out from that catchment, from these catchments. Okay, so getting a little bit longer term, many fires have been studied for a few years, and our Hayman study, that was the previous work I showed you here, that was the sort of the 5-year record, and that's a pretty common time frame for people to look at fires. And after that, a lot of times people forget about it, they go on to something else, they study a new fire or so on. Well, we ran out of money following our first 5-year period, but came back with another chunk of money and studied those same streams after the Hayman fire in years 14 and 15. And frankly, we expected that we were going to just close the book on it, show that things had gone back to the pre-fire conditions. But what we found was not that at all. So what I'm showing here are various forms of nitrogen in the upper parts here across various seasons. So in the early part of the stream hydrograph, following the falling limb, and then in the base flow conditions. And you can see the various colors are associated with levels of high severity burning. So our extensive high severity areas remained 5 to 10 times higher for 2 different forms of nitrogen in the streams. And our moderate, these were areas that had about 30 to 60% of the catchment burned. Those were, or I'm sorry, less than 30%, were also significantly higher, even 14 or 15 years after the fire. Now, the interesting thing that you should think about is that prior to the fire, almost all the nitrogen that came into that system stayed there. In other words, most of it was retained within the vegetation. There was a very little amount that leaked out the bottom. Over 95% of it stayed in that ecosystem. Following the fire, however, more than half of what came in went out. So in other words, we went from a system that retained nitrogen to one that was very leaky and lost a lot of the nitrogen. And that change in sort of the way nutrients are retained is kind of a key piece I'm hoping that you'll take away from this. Okay, so another new piece of information, sort of thinking about some of the reasons why we might see these long-term effects. This comes from a PhD student from the Colorado School of Mines, Alex Honeyman, who worked down on the 416 fire and also on the Decker fire. And he's doing some very, very complicated high-tech microbial, soil microbial analysis to be able to actually, he's doing a lot of looking at what organisms are within the soil community, but he's also using a new technique to actually look at the biomass, the amount of those different soil microbes, either bacteria or fungi. These are important to us when we think about watersheds because these are the things that process and take up nutrients, that either transform it from an organic form or that suck it up and keep it within those systems. So this is a way of sort of looking at the function of the soil of the soil nitrogen cycle. And what you can see, I know the labels are sort of small, The far left on all of these is our high severity burned areas. We're talking about the organic layer and the mineral layer in both of these cases for these two different groups of soil fungi or the soil microbes. And he's got 3 different years. So the year of the fire and then 2 subsequent years. And what I'd like you to look at is how the high severity fire really kind of zeroed out the soil microbial processes in both the organic and in the mineral soil for both of these groups of organisms in the first year, but also that those areas start to bounce back pretty quickly. So year 1, they're no longer in the basement there. And in year 2, they're getting up to levels that are comparable. It looks like in some cases, they may still be depressed relative to the unburned or the areas that had burned at lower severity, but they're certainly responding. So that suggests that the soil communities may be fairly resilient to fires and that they may recover fairly quickly, which is good news because that means that the processes that supply nutrients to plants, that take up nutrients and hold them on the site are getting back to normal. And so some of that retention process is probably returning. Okay, what about streams? So we know that you have fish kills, you may have various things happening in streams that may sterilize them following a fire. Well, in our neck of the woods, we see a lot of algae coming in following fires. So it seems like that's probably not a likely situation. And this slide sort of shows evidence it's probably not really what's going on. So for example, if we look at the production within streams and look at the amount of algal production, what we see is that burned streams are actually more productive than unburned streams. They're not less productive. They're not sterile. They're actually growing more algae or periphyton or biofilms. And basically, that means that there's more nutrient retention in stream. So the retention piece within the stream is actually elevated thanks to the stream biota, but they don't really grow high enough to be able to sort of scour the nutrients that are being exported from the upland areas. So they have increased. They're certainly not sterile, but they don't grow that much. And I think if you're concerned with things like algae and water treatment, you probably don't really want that anyway. Okay, so what else might be responsible? One of the sort of obvious things that we see, and this is a picture from the Hayman fire, but we see similar patterns in a number of the fires along the Colorado Front Range that have burned in the last decade or so. What we see are these large areas that are very slow to recover. This is a ponderosa pine forest. This part of the Hayman fire burned at high severity. This is a fairly large patch of high severity. And what we see in this diagram is kind of describing this photo here using NDVI, which is a remote sensing tool that is an index of the greenness on the landscape. So you can see what an unburned system would look like in terms of years and what that would be down on these forests. So this is a healthy ponderosa pine forest, we might say, and then you can see what happens following the fire, where the greenness crashes, it becomes a blackness, and both in the upland areas and also down near the streams where it burned at high severity. The important point is that even though it's coming back, it's really taking its time. And you can see that there's something growing out here, and there agave and there's a lot of grasses and forbs on this landscape, but there's a lot of bare soil. And there's certainly not many trees. Many of the trees that are out in these areas have actually been planted by the Forest Service to try to regenerate these areas. But if you look at the patterns that we've seen, it's going to take another decade or so to kind of get back to where things were prior to the fire. So the idea that vegetation is kind of a key piece to the nutrient uptake is kind of what we're getting at here. Another sort of facet to that is what we've seen with riparian areas. I showed you a picture of some of the riparian NDVI. These are some areas in the Hayman fire where we see good riparian recovery or low riparian loss compared to areas where there's very little riparian cover. And the intriguing piece is that the more riparian area you've got, or conversely, the less riparian vegetation you've got, the higher your stream nitrogen. And this is an additional slice of evidence that says that the vegetation is actually helping to take up or retain nutrients in the site. So in other words, if you have a very low amount of riparian cover, you're releasing more nutrients to the stream. This is interesting, and it also has important implications if we're thinking about watershed restoration and where we might actually think about planting. So the status quo is typically to replant upland areas with commercially valuable timber species or timber species of interest. Another approach might be to actually think about trying to create habitat and nutrient retention in lower parts of the landscape. These are areas also where there are important wildlife corridors, areas of high native biodiversity, potentially areas of concern for invasive species. So good areas to be actually focusing restoration attention. Okay, so to kind of conclude, wildfires are a native part of our ecosystem, and we've all learned in our ecology classes that ecosystems require fire in some cases to regenerate. And so what's the big deal here? Why are we kind of talking down about fire when we know that? And you probably have heard people saying we need to reintroduce more fire, and isn't this something that we're kind of speaking out of both sides of our mouth about? And that's actually correct. We're starting to think about various types of fire, and some of the things that we've been seeing in recent years where we've had fire in conjunction with stressful climate conditions, which may be novel. The strength of some of these droughts that we've been having are new and unprecedented. And we've also been seeing fire in conjunction with other disturbances. Up in the northern part of Colorado, there have been a lot of fires that have burned in bark beetle forests, and that's an area of important research and interest where we really don't know what that combination is going to yield. So there's a lot of important value to wildfire, but some of these new conditions may actually be pushing things in directions that we don't understand and maybe aren't going to be too crazy about. So to finish, I just wanted you to think there are various sort of time frames to think about with wildfires and that influence water quality, and some of them are happening right off the bat and during the fires themselves, from retardant during the suppression, and maybe things like bulldozer lines and so on that might create erosion. There's something on months and maybe years where we see that sort of ash mobilization, and and sediment loss. And then there's also this sort of much longer term phase, which could last decades. There's no reason to think that it wouldn't, as forests recover and may become, may actually become novel systems. And I think with that, I'm done and will happily pass the baton on to Scott. Let me see if I can stop sharing. Okay. How did that go? Can anybody hear me there?
Chuck, this is Scott. That was great.
Good. I just hate to think that maybe I just gave that talk and nobody heard it for myself.
Right. Yeah. Thank you. Emily, did you have?
Jar.
Did you want to jump in, or would you like me to go ahead?
Yeah, you can go ahead and keep it going, Scott.
Okay, great. Well, let's see. I'll go ahead and share my screen. Let me know, Emily, if you're seeing it.
Yeah, we're good.
Oh, great. Well, Chuck, thank you for that. That was really informative, and I think sets the stage very well for what I'll hope to do is build on the concepts that you introduced, and maybe give a kind of site study examples from our local most recent fire, the 416 fire, and kind of dial in on the impacts to water quality and aquatic life we've seen thus far. There we go. So it's a research team that I'll be speaking of scientists from Mountain Studies Institute and Rocky Mountain Research Station, including Chuck Rhoades, who you just heard from, and scientists from Colorado School of Mines, Dr. Ashley Rust and Dr. Terry Hogue. And what we're aiming to do with this research is to try to figure out what the magnitude and extent of impacts to water quality and aquatic life and habitat for aquatic life occurred following the 416 fire, and what recovery looks like, or at least what the transition after the fire looks like from year to year as we get further away from that 2018 fire. And our research has, 4 broad research components. The first is instrumentation. We deployed some continuously monitoring water quality devices that continuously measure water quality parameters such as temperature, pH, turbidity, dissolved oxygen, conductivity. We enacted a water quality sampling regime where we went out and grabbed water quality samples across different hydrologic regimes, including kind of pre-runoff, during the spring runoff in kind of the May-June time period, fall and base flow, lower flows, and also during storm events, which of course necessitated us doing some unusual sampling where we'd have to go out at 1, 2, 3 in the morning to catch storm pulses coming off the burn area and down Hermosa Creek into the Animas River. And then we assessed aquatic life habitat, the stream bottom where aquatic insects and fish call home. And lastly, looked at aquatic insects as indicators of overall health of aquatic systems. And since benthic macroinvertebrates are a large focus of my research, I'll give you just a little overview of what those are in case anyone out there is not familiar with them. I hope most people are. But these are called benthic macroinvertebrates. And benthic just means they live at the bottom of streams and lakes. Macro means that you can see them without the aid of magnification. Invertebrates, of course, they're animals without backbones. And they're an integral part of the food web. They're an important food source for fish, birds, spiders, and additionally, they're really excellent indicators of changes in water quality. When we go out and take a grab water sample, the actual water sample container and the water in it is really reflective of the conditions at the time you took the sample. When you go out and look at a bug community, those insects have resided there for weeks, months, even multiple years, and been exposed to a variety of conditions that have happened over that time period. So they're more reflective of a longer term water quality trends. And they're closely tied to those habitat, both in the water column as well as on the stream bottom. And they're really diverse, which is useful because you can look at the proportionality of the community composition to look at the types of insects that are sensitive to water quality perturbances, and those insects that are accustomed to maybe highly sedimented environments. So we've couched our assessment really as looking at, much like Chuck did before and after studies, so pre-fire versus post-fire, and then also looking at burned sites and unburned sites. And here is a map depicting where our research sites are. There in the beige is the 416 fire perimeter, centered around Hermosa Creek. And you can see with those red dots that we have a number of burn sites within the burn area where we're collecting information. We also have unburned sites that are above the burn area and also adjacent to the burn area on the Animas River, and then notably on Junction Creek, which is just south of Hermosa Creek, another tributary to the Animas River that we're using as somewhat of a paired comparison, comparing the burned Hermosa Creek site to the unburned Junction Creek site. And then lastly, the yellow dots downstream of the fire on the Animas River. And these are sites downstream of the fire that are exposed to sediment and potential contaminants that are mobilized out of the burn area and flushed downstream. So what do we see? let's see, what did we see? Well, I'd like to show you some videos of how, what some of the most profound impacts to aquatic life occur post-fire. And let's see, I'm gonna try to change my screen here. And hopefully everybody goes with you. Emily, shout down if it's working. Okay, good. Emily's just upstairs in the same office. This is from a researcher at the University of Arizona. It's not from the 416 fire, but it's from a fire in Arizona. But it really is a strong capturing of these debris flow events where rain events occur and move sediment down. And move sediment down these ephemeral gullies. And let's see, are you still following? Thank you. And here's another one. Yeah, the researcher's name there is at the top. This is Luke McGuire at the University of Arizona. But just to give you a sense of how much material is mobilized in these ephemeral gullies, trees, boulders, rocks, and a lot of debris and potential contaminants moving downstream in these ephemeral gullies and being deposited into perennial streams. And I'm going to attempt to take us back to my presentation. And we saw evidence of this all over the 416 burn area, as evidenced by these gullies that seemingly opened up in the earth, and clear indication of a lot of material that was mobilized downstream and into Hermosa Creek and into the Animas River. Here's one where it eroded down to bedrock. This is looking down one of those gullies, and you can see the scars on the spruce trees where trees and boulders and rocks had come down in those debris flow events and battered the trees. And when they hit confluences or low gradient reaches, log jams often accumulate. And what's notable for aquatic life is what happens, in addition to the log jams adding woody debris to streams is what happens behind them as the gradient of the water backs up, and a lot of sediment and debris and silt and sand is accumulated, fundamentally changing the habitat for aquatic life. And so how do we get at that with our surveys? Well, first I'll talk about the stream bottom and how that material accumulates. And so we look at transects across a reach of stream channel and measure 105 different places along the channel and measure the actual substrate, whether it's fines or sands or cobble or boulder or pebble or gravel. And here I'm simplifying and characterizing in these four categories: fines, sands, cobble, boulder. In this top picture, you're seeing aquatic habitat that's largely sand. And then the bottom picture, you're seeing aquatic habitat that's largely more of a cobble boulder size. And here I'm illustrating our findings before the fire in a site on Hermosa Creek. And this is an 150 meter stream reach depicted with proportionality of the substrate size classes. And there you see, prior to the fire, a system dominated by cobble size substrate, which is the preferred substrate sat category for mayflies, stoneflies, caddisflies, and kind of higher diversity of aquatic insects inhabit the cobble sized substrate. And the fines and sands, you can see pre-fire were pretty minimal. And then here is the results from our 2018 survey, where you see a great increase in fines and sand and a reduction in that cobble size substrate. So real profound changes in substrate in the habitat that's available for bugs and fish. And we also looked at the water column, and I'm going to show you another video here. This is of Hermosa Creek that someone captured during July of 2018, right after the fire, after one of the largest storm events rained in the burn area. And obviously this is typically a pretty clear colored River has been designated outstanding water quality by the state of Colorado, harbors native cutthroat trout. And so you can just imagine that the conditions you're seeing in this video are quite abnormal for this system with large trees moving downstream and such. So how does this affect aquatic life? Well, as you can imagine, just the mud and clays and debris moving downstream can physically just abrade gills, clog fish gills, tear fish gills, and insect gills. There can be potential contaminants in that water that could cause toxicity. There could be sublethal effects where perhaps some aquatic life can survive those conditions, but they have reduced growth or perhaps reduced reproductive success, or changes in food resources, where those insects that are dependent on algae, if algae is removed in those events, it's a change in food resource. Or if riparian forest is burned, those shredding insects that are dependent on terrestrial input of riparian tree species like willow wouldn't have that food source anymore. So in general, we saw much like Chuck talked about in the from a great work by Bryce Pulver from School of Mines, I'm sorry, at CSU, who found that the metal concentrations of tributary streams within the burn area increased in metals during the fire. We found that downstream of the fire in Hermosa Creek and down into the Animas River, really a similar story, where degraded water qualities, especially in storm events, and we saw large increases, 10 times, 3,000 time increases in sediment and nutrients and metal. And so I always ask the question, so what? What if there's higher levels of some of these things? And I like to think about it in the context of two things. One, is there a precedent for it? Is it typical to have those high concentrations of some of these water quality parameters? And then secondly, is it ecologically relevant? Can we use toxicity data or water quality standards to determine whether those high levels are indeed detrimental to aquatic life? So I'll run you through an example here. Excuse me, this is total aluminum at the Animas River in Durango from 2002 to 2020. And those gray dots are data largely from the Colorado River Watch program, which we're fortunate to have in this state to collect a lot of great baseline data. But you can see we've got data going back to 2002, and then some of the more recent data is data we've collected from MSI. And part of this context of water quality history in the Animas River now, of course, includes the Gold Key mine release that occurred in 2015. And you can see some of those higher concentrations, in fact, the highest concentrations through 2018 of total aluminum that we'd ever seen, of course, happened during the Gold Key mine release. Well, here comes the fire, and then these orange kind of yellow dots are water quality samples that were collected after the fire. And you can see we detected pretty high levels of aluminum. In fact, higher levels than we'd ever seen before, even higher than what was observed during the Gold Key mine release. And so, yes, unprecedented levels of some of these contaminants or potential contaminants. Those highest concentrations are from storm events that are largely occurring in July and August, maybe one in September, but most of them in July and August. And now in terms of kind of looking at water quality standards, CDPHE has water quality standards that they've established based on toxicity experiments, and they have them in two categories based on the exposure of the contaminant. There's an acute water quality standard, which is set to protect aquatic life in the Animas River from brief short-term exposure. And then there's a chronic aquatic life standard set to protect aquatic life in the Animas from persistent long-term exposure. And what you'll see is that there's instances where we're exceeding both the chronic and the acute water quality standard for total aluminum before the fire. But if you look at the top line, the acute water quality standard, the yellow one, you'll see that the only time we had exceeded in the past that standard was during the Gold Key mine release. But then in every year since the fire, we've had multiple exceedances of that acute water quality standard. So just to kind of summarize across, at least in terms of metals, possibly unprecedented levels in the Durango stretch of the river of aluminum, manganese, iron, and mercury. and concern for risk to aquatic life for acute aluminum, chronic iron, and chronic lead. So that's what toxicity experiments would tell us. What do we actually see in terms of impacts to aquatic life from the 416 fire? Well, during the fire, during the actual heat of the fire, when there's fire on the ground, there can be impacts to aquatic life, especially in localized smaller streams where, like in this picture, fire burns right up to the water's edge. And fortuitously, Colorado Parks and Wildlife had deployed some water temperature sensors in some tributaries of Hermosa Creek that ended up burning. And they were able to retrieve those sensors after the burn and actually successfully retrieve the data and see water temperatures that generally were at 55, 60 degrees Fahrenheit, drastically increased to over 80 degrees Fahrenheit in a matter of minutes as the fire, came across the stream channel. And that can definitely be stressful, if not lethal, to certain fish and insects. But most of the impacts to aquatic life are really associated with those post-fire runoff events where a lot of that material is mobilized downstream. We unfortunately had a couple of fish kills, likely in Hermosa Creek and definitely documented in the Animas River downstream of the fire. Something that I think is really fascinating is downstream of Durango is the Southern Ute tribe, and they have a really robust environmental monitoring program where they look at water quality and aquatic life, fish and bugs. And one really smart thing they did was when these rains were coming after the fire, they went out and did some aquatic insect surveys in the Animas River, and then the debris flow occurred, fish kill occurred, and saw a lot of material mobilized and moved downstream. And then they went back, just a few days later and resurveyed those same reaches of the Animas and found that the aquatic insect that was dominant beforehand, this Baetis blueing olive that's in this picture here, disappeared from the samples, completely gone. It went from being the dominant species comprising some 80% of the community to being completely absent. And what they caught there in their data is a massive drift event. So baited mayflies are known to drift downstream in response to unfavorable conditions. And so as the river became very turbid and unsatisfactory to aquatic life, they would pick up off the bottom and drift downstream in search of better conditions. And so it's really an interesting response from those debris flow events is these mass drift events from insects that would try to move downstream in search of better conditions. So there's lots of before and after data that I'm going to talk about now, pre-fire versus post-fire. In terms of fish, Colorado Parks and Wildlife did some fish surveys before and after the fire in 2016 and 2018. They looked at the number of fish per 1,000 feet. And you see here these enormous reductions in brown trout and rainbow trout associated with those fish kills. Fortunately, the bluehead sucker is a native fish, and there were lesser impacts to that fish, perhaps more resilient to these type of events. We'll see. On the good news front, Colorado Parks and Wildlife did some fish stocking surveys on some tributaries to Hermosa Creek within the burn area, and I was able to accompany them, and we were able to catch some native cutthroat trout that had survived, notably the San Juan Lineage cutthroat trout. We were lucky and happy to see that many of them had survived the fire. In terms of aquatic insects, what we really saw, after the fire was a departure from pre-fire conditions. Really a strong shift in the community composition and reduced diversity. And I'll illustrate that here in a similar kind of river diagram that's depicting the reach that we surveyed of Hermosa Creek downstream of the fire. This is again pre-fire data from 2016. And what I want you to hone in on here is kind of this blue. The light blue is mayflies, the darker blue are stoneflies, and the purple are caddisflies. And those three categories are really your kind of main groups that you look at that are great indicators of good water quality. And then true flies in the yellow there are usually more abundant in stressed systems. They're happier in heavily sedimented areas. And then here's 2018 after the fire, and you can see a clear shift in the community composition as those blue mayflies, stoneflies, caddisflies reduced in their relative abundance in that community, and it just really became dominated by these chronid midges that are categorized as true flies. And we saw this pattern persist, down outside of Hermosa, down into the Animas River and down to Durango, but they seem to that pattern seems to diminish the further you get from the fire. And so the other question we asked was if aquatic insects were able to survive this event, were there sub-lethal impacts? And so what we did was look at the metals in the insect tissue to see what their body burden was. And sure enough, we saw pretty large increases in aluminum, iron, and lead and aquatic insects downstream of the fire. So did we see, it's 2021 now, and we've conducted these surveys in 2019, 2020, so 2 full years out of the fire that occurred in 2018. Have we seen recovery, or have we seen a trend back toward pre-fire conditions? Well, I'm going to show you a series of kind of repeat photos. On your left is 1 year after the fire, and on your right is 2 years after the fire. And in this instance, you see a kind of sand deposit on the bank of Hermosa Creek here, and on the right you see it's largely been mobilized and moved downstream. Here's a stream bank on your left that was stripped of vegetation, and likely a lot of sediment was deposited, and you can see it revegetating quite well and stabilizing on this small tributary. Similarly here on this repeat photo, you can see revegetation and stabilization of the stream bank. But there are some places where there was so much sediment deposited that really even 2 years after fire, you're not seeing much revegetation. There's some terraces that were formed as water during those flood events moved out of the banks of Hermosa Creek and formed these kind of depositional terraces that are starting to revegetate. And it'll be interesting to watch as the channel may move back into its prior location, and this revegetates over time. This is looking down some steep gullies where a lot of material is mobilized and moved down into Hermosa Creek, and you can see at least some level of revegetation of that area. Here's a bank of Dutch Creek, which is a tributary to Hermosa Creek in the burn, and on your right you can see quite a bit more vegetation as those stream banks are revegetating. Despite the cows being there in the exact same location 2 years in a row. Here's an instance where on your right, you can see on the right hand side of both pictures, a large boulder, it's a very large boulder, crashed down the hillside and into the stream channel, which I find interesting. And in some cases, you're not just getting an influx in small size sediment, sand, and fines into these stream channels, but you could have some reorganization of the stream channel where boulders come down and could form pools that actually could be good for fish and provide a refuge and some pool habitat. Similarly, here's a tree that fell across a small tributary, adding woody debris that will be a food source for some aquatic insects and some refuge and cover for fish. And lastly, here's another tree that you can see fell across the stream channel. In this case, this is Hermosa Creek near the South Fork of Hermosa Creek, where the tree fell in and will have influences to aquatic life. So what did we see in terms of recovery? Well, it's a mess, as you can imagine. Here I'm trying to illustrate that by showing you all these different multiple lines of evidence starting at a pre-fire condition and then departing from that pre-fire condition in multiple different directions, some increasing, some decreasing, some making their way, trending back toward that pre-fire condition, and others not. And then I'll show you a couple examples of what I'm talking about, but here's total lead starting out at the pre-fire condition and departing rather dramatically, increasing in 2018, but in 2019 and 20 returned to pre-fire condition. Others had an opposite. Other lines of evidence we looked at in this case is the percent composition of simulium black flies downstream of the burn area, and you can see just immediate departure from the pre-fire condition and no sign of turning back yet. And that's an interesting phenomenon. And then several metrics that departed from pre-fire condition and then started trending back toward pre-fire condition, but haven't made it quite back there to be considered that some would consider recovery. Yeah, but in general, what we've seen is we're still untangling. We're still untangling all these different lines of evidence we're looking at and elements of aquatic life and their habitat. But we're largely seeing improved habitat, of flushing of sediment, cobbles emerging. In terms of water quality, most of the contaminants were highest immediately after the fire, and we're seeing concentrations of some of those potential contaminants lessen over time, as expected, and fewer water quality standards exceedances in 2020. However, most of those parameters that are most of concern are definitely still above pre-fire levels. In terms of aquatic insects, we're seeing that, they're after that large shift in community composition, they are trending back toward pre-fire community composition, but there's still low diversity, and in the body burden and the tissue metal concentrations, they're still elevated in 2020, 2 years after the fire, above pre-fire levels. So we have more to come on this, but it's a beautiful place, and I do want to say that fire is an integral part of our landscape, and it's important for our forests and ecosystems, and it can be a beautiful thing. So it's not all bad. And lastly, I just want to thank a lot of people, including our community and especially private landowners who granted access to some of these sites. We really appreciate that collaboration. And then people who have and organizations that have funded this effort are many, and we appreciate that support across the community, from the likes of City of Durango, Animas Water Company, CDPHE, Colorado Healthy Rivers Fund, CWCB, the Community Emergency Relief Fund, the Southwestern Conservation District, and Trout Unlimited. And with that, I think I'm done. But I think what I understand is that we'll open it up for questions for both Chuck and I, and that sounds great.
That was great, Scott. Thank you so much. So we've got some questions lined up here. Let's see. So our first one here is, how much nitrogen in aquatic systems is typically actively tied up in decomposition processes? So Chuck, that might be a question for you.
Yeah, that's a good question, and it's probably something I don't have a good answer for, unfortunately. And Scott might be able to help. I mean, a lot of what I was showing was autotrophic production, so not by decomposers or heterotrophs. When we do the sort of nutrient diffusion studies, which we use to sort of get at that stream productivity, the streams have a lot of heterotrophs in them. So things that are relying on carbon from outside of the system. And so they take up a bunch of nitrogen, but sort of the breakdown of that, I don't think I could be able to tell you, and how much of it is actually tied up in decomposition. I'd have even less of an idea, but Scott, you might have an answer for that.
I don't, Chuck. You're the chemist. You're the biochemist.
I'm not a stream ecologist, though, so that's my excuse.
No, that's only good.
And I believe that was actually a two-part question. So the second part to that is, how do large fire events impact this part of the nitrogen cycle? So I'm not sure if that's something y'all can tackle.
Yeah, I mean, I would have less of an idea of that. I mean, so part of the thing, and I think Scott touched on it in his talk, I have it in part of my slide. One of the things that happens with decomposer food webs, you stop getting litter coming into the streams, and a lot of them become a lot more sort of, disturbed and down cut, and you don't have some of those, areas where you're getting constant inputs from fine litter. So I could see how fires might have, effects on, because you don't have a, riparian vegetation, would have effects on some of those easily decomposable materials. Similar, but on the other hand, you're having things redistributed. Scott showed some great pictures of wood being moved around. A lot of that sediment and organic matter that were in the channels and upstream end up in sort of depositional areas. So it seems like there may be a bit of a sort of a reorganization, but in terms of sort of the intact, just sort of decomposition situation where you've got litter coming in, you've got a sort of a stable food web in the stream bottom, that could be a sort of the top might be torn off of that by these big high severity fires.
Great, thank you. We have a question in here in Facebook from Marcel Jean, who says the Bear report found that only 6% of the 416 burned at high severity, but we still saw pretty remarkable increases in nutrient levels downstream of the burn. Does the reported low to moderate burn severity of the 416 track with the water quality impacts we saw in the Hermosa and the Animas rivers?
Yeah, that's a really great observation. And something that I had noticed is, one of the things that I found really intriguing about the 416 fire, not only was a lot of it at low a lot of it at low and moderate, most of that catchment didn't burn at all, right? And I don't have the numbers in front of me, but Scott can talk about it. A large amount of that area, and his drawing showed there was a nice section of the stream above it that didn't burn at all. So I've been surprised by that, to be honest with you. So it doesn't necessarily agree with other fires per se. And in other words, we have a fairly large response for a burn that was fairly low, but I would probably sort of look at it and tear apart some of those tributaries and see of the ones that burned are the high severity ones, the ones that had more higher moderate, the ones that responded the most. In other words, if you look at it within the fire, does that pattern hold true? I think that's an important observation, and part of the other piece of that, we've looked at some of the nitrogen in the 416 fire, and it doesn't appear that it's starting to sort of recover right away. So even a couple of years after the fire, it's still high. So that suggests that it's acting like a more aggressively burned forest as well. I would in most cases, we lump high and moderate together. And so I guess if I was going to address your question more carefully, I'd want to know, because I don't remember off the top of my head, I can probably find it quickly, how much of that was actually moderate, because I would sort of say that might be a good indication as well. Scott might know that.
Yeah, that's a great question, Marcel, and Chuck, I think you covered it well. One thing I would add is that Marcel, you know this well, that fire happened in 2018, a significant drought year. The following year was a big snowy year, lots of water coming down the river. And then 2020 was another drought year. And I think that, Chuck talked about it earlier, these compounding, overlapping disturbances that I think that, beyond just fire severity, just the overlapping disturbance of a fire followed by drought could exacerbate some of these impacts from the fire and lengthen the time it takes to see levels return to pre-fire conditions.
Great. Let's see, Michael Rimke has a question for you both. So he wrote, Chuck presented on a variety of different fires that included some mixed severity fire and some very large, high severity fires, whereas Scott presented a nice narrative of one specific fire that burned at mixed severity. I'm curious, could both of you gentlemen share how your data fits into what we would expect for stream/soil responses in the historical range of variation of fire? Are these patterns you presented enhancing our understanding of post-fire processes in the ecosystem? Or are we seeing unprecedented and unexpected outcomes as a result of altered fire regimes, et cetera? Thanks. Sorry for a long question. Thanks, Michael.
Thanks for the prelim question, Mike. So that I think that's an interesting observation, and I definitely think some of the fires that I've studied are on the edge, and the Hayman fire is an obvious one. The size of those high burn patches are fairly unique, and that's something that we've seen kind of a number of those along the Front Range. So I think those are sort of pushing that envelope a little bit towards something that's a little extreme. And there's clearly controversy about that point, and I'm sure that people would disagree with that for sure. Yeah, and Scott maybe would like to say something about 416 and that fire. I mean, I can talk a little bit about some of the other fires up here in the Northern Front Range that we're now studying that I wasn't reporting on with regards to the bark beetle and the fire severity piece, which I think is another aspect that's I would say pushing the envelope in a kind of a completely different direction. I think we've talked about that with what's going on below ground, where you have hosts that have been dead for a long time. I think we're seeing some unique opportunities to study and advance our understanding about below ground role in sort of fire recovery.
Yeah, I'll just add, thanks for the question, Mike. I would just add that I think what we expect to see from the 416 fire, given that it was predominantly low and moderate burn, would be that it would return to pre-fire conditions, and at least in terms of aquatic systems, readily quickly. And I think that's something we were hoping to demonstrate, that fires like this could return to pre-fire condition relatively quickly. And then in addition to that, one thing that we are documented that isn't unprecedented, isn't the right word, but undocumented previously maybe is the right word, is the uptake of metals by aquatic insects hasn't been documented, in other fires, and is an interesting kind of flux of metals through, could have cascading effects through the food chain.
Yeah, and I think that's a really important point, Scott. And I think that's another thing to keep in mind. It's not just the fire, it's what water quality constituent are you interested in. And if you've got a fire like the 416 that has this big metal response, it seems really clear that the water quality and the downstream effects are going to be different than, say, what we saw at Hayman, where the problem was nitrogen, an increase in carbon, and a few things, but not serious metal problems. So it's kind of, an apples and orange thing. You have to think about what water quality constituent do you have, and I think that's we're becoming more aware of metals following fires, even in areas where there might not be a lot of mining, places where there's deposition. And we know from some of the fires on the Colorado-Wyoming border, there have been long-term deposition from mercury that are downwind from coal burning plants, and moving that into aquatic food webs has, is important implications that I think Scott's work and Bryce's work and Ashley's work shows that these are things that people should pay more attention to. They're not, they're probably more widespread than we've been sort of giving them credit for.
All right. Awesome. I think that was our last question. Thank you everyone for hanging in with us as we got to some of those really great questions. Thanks again for throwing those in the chat. I'm going to go ahead and want to share my screen, see if this works on my end, but let's see. There we go. All right. Very cool. Thank you. All right, folks, I just want to say thank you very much for joining us this evening. And we really look forward to seeing you again next week as we learn about how agencies develop proactive strategies to the challenges that were faced in 2020 and how they are using those lessons moving forward this year in this fire season. So, and before you leave, please be sure to fill out the surveys that are in the comments section, especially if you'd like to win a combination of one of these totally awesome prizes. And thank you very much again to our sponsors who donated all of these items for the Forest and Fire Learning Series. And of course, thank you to all of the supporters of the Forest and Fire Learning Series. We really do appreciate you and you really make this possible, this event possible for our community and beyond. Of course, I want to say thank you, of course, to Dr. Chuck Rhoades and to Scott Roberts for sharing all of their research and their findings. And we really look forward to hearing more in the future on your research and your data. And we appreciate all of you tuning in, and we look forward to seeing you again next week, same time, same place. Bye.
Thanks very much.